Good morning, good afternoon, good evening. Thank you everyone for being here for your module 3 of the 3-month hands-on certification program in pharmacometrics and PK/PD modeling using RsNLME. So today we actually will be getting into the RsNLME and then in the following workshops, we would actually get deeper into the concepts and the use of this tool. As you know, today's workshop is hosted by Project Dontabhaktuni and is sponsored by Certara, who are the makers of this tool, RsNLME, and Pharma Pro Consulting. You, of course, know of me. So today, I actually would like to invite Anna Henry to introduce our today's speaker, as well as your developer for RsNLME. So Anna, would you like to introduce our today's speaker?
Yes, good morning, everybody. It is my pleasure to introduce today Dr. Keith Nieforth as the main speaker for today's lecture on the introduction to RsNLME. So that is Speaks NLME. Dr. Nieforth is the product owner for Certara pharmacometrics software like NLME, Piranha, Trial Simulator, etc. And prior to having the pleasure to have him at Certara, he was at Roche for over 20 years in the clinical pharmacology department, where he was involved in numerous PK, PK/PD, population PK analysis. Keith holds a Bachelor of Science degree from the University of Connecticut and a PharmD from the Massachusetts College of Pharmacy. So welcome, Keith.
Thanks, Anna. Thanks, Anna, and good morning, good afternoon, good evening to everyone. I'm very happy to be here to share with you the work that we've been doing probably for about the last 2 years to build RsNLME. Again, I wanted to acknowledge the help of Anna, of course, and I know a lot of you have spent some time with Muli on the installation. Wanted to thank Muli again for supporting that. And if anyone still has issues with some of the installation, you know, we can hold another session. I did want to mention that also in the audience is James Craig, who is our developer. That essentially, you know, I have ideas. James is the one that built many of the tools that you'll see today with his team. So we'll go ahead and get started. This is the agenda for the 3 sessions that we'll have today. What I wanted to do is spend some time talking about the background. You know, why did we build RsNLME? Why do we think that there's, you know, a need for this type of tool? And I'm going to put that in the context really of the, you know, the pharmacometrics workflow, right? We've heard about the theory. We've learned a bit about R. What I want to talk about is the job, right? And how the tools that we've built support the job. I'll give an overview of RsNLME and Piranha. And we're going to focus mostly on the use of Piranha because it makes the use of RsNLME easier. But as you'll see, you know, everything you do in Piranha can be done from the command line. And Piranha, in a way, can teach you, as well as the apps that we've built, can teach you how to work in the command line simply by going through the steps in the workflow. I'm going to start with a data set and go ahead and just jump right in. We're going to open that in Piranha, do some data inspection, check for errors, you know, get a sense for a starting model. I'll show you some of the functionality of the Piranha data inspector, which is like, it's kind of like a quick and dirty tool that allows you to quickly assess, you know, your initial data set. But then what I want to do is actually show you a demonstration of an open source package in R. It's called ggQuickEDA. This package was built by one of our consultants here in Certara, Samir Muksasi. He's one of these amazing guys that he's a consultant and software developer kind of rolled up in one. But this is a GUI, it's a GUI interface to the ggplot2 package. And this tool, like many of the Shiny apps that we've built, allow you to do what you need to do through a graphical interface, but then we'll return the source code in R, so you can run that at the command line. So tools to teach, right? It's kind of a concept that you'll see recurring through this presentation. After we do our data inspection and have an idea for our structural model that we want to start with, and perhaps an idea of what types of covariates might be important from our exploratory analysis, I'm going to go back into Piranha and we're going to start modeling. And there we'll take a look at the RsNLME model builder. I'll pause because Anna is going to give a basic overview of the pharmacometrics, Certara's pharmacometrics modeling language, PML. Again, we could give a 3-day course on probably each one of these subjects. So what I'm going to try to touch on is really the core important kind of core pathway. So you understand like the big steps, and then at any step over time, you can kind of get deeper and learn more, and eventually become proficient in doing pharmacometric work in R. And then finally for today, we're going to fit a model and then look at some of the functionality within Piranha to generate diagnostic goodness of fit plots, take a look at key diagnostics that are packaged within Piranha, and show you that for any of these diagnostic plots in Piranha, you can actually open these within R and customize them to your own need. And that's, again, that's kind of like a key key reason that we built all of these tools on R. Any graphical user interface tool that you might work with probably handles the core part of the analysis very good, and can be efficient, with that. But the reality in drug development, particularly early drug development, is that the information that you have is only as good until the next piece of data comes in. If you ask any early development scientist, how would you do this? What features do you need for this type of graph? The answer is not going to be, well, I need feature XYZ and you can build it and everything's fine. The answer you always get is, well, it depends. And I think that's why tools like R are so popular, because you have infinite flexibility to customize to your exact problem. So building these tools on the foundation of R and making it easy for users to work, and then, okay, if I need something special, I'll just do that in R, is a big advantage. And again, partly, I think, the reason for the popularity of R in our field right now. We're going to provide some homework. Again, this homework, really is to touch on completing the core elements of a workflow in using RsNLME. And then session 2, we're going to continue on and take a look at assessment of covariates, how to incorporate covariates into the model, and then look at some model validation techniques, simulation diagnostics like visual predictive checks, and we'll take a look at our tidy VPC package, which greatly simplifies the creation of those type of diagnostics. And then we'll create a data set and run a simulation with a new dose regimen for our model. And then at the very end, what I'd like to do is then, again, I'll be doing most of this using Piranha, but what I'd like to do is just jump over into R and give a demonstration of a full end-to-end population PK analysis. So, all right, so what is RsNLME? So RsNLME is a collection of R packages, open source R packages, and companion RShiny apps that allow pharmacometric scientists to run models using Certara's NLME engine directly from the R command line. And basically, RsNLME was designed to provide a Certara supported environment for pharmacometric work in R. An analogy would be, something like the tidyverse in R for data wrangling, For those of you familiar with, somewhat familiar with R, Tidyverse has been being built up over the last several years and is really a nice collection of packages for data management in R. So what we're building is a set of packages in R. Yes, they are based on, Certara's NLME engine, but they're designed to work together to allow users to work with pharmacometric models in R. And, again, this set of packages in the open source world, we can support it in Certara, which is important for organizations, right? Just a very quick story. When I was at Roche, S+ was the precursor to R, and I had spent a lot of time becoming proficient in S+. So from my department, I was kind of the S+ expert, and people would come to me when they had problems, and usually I could help them. One day, someone walked into my office and said, "Keith, my S+ is doing this," and I looked, and something was corrupt. And I was like, I can't really, I don't know what's wrong with that. You need to call IT support. So they're like, okay, I'll go call the company IT support. So I get back to work, and like 10 minutes later, my phone rings, and it's IT support, and they're saying, "Yes, Keith, someone has a problem with S+." So it went in a big circle. And again, when you work in these open source environments, right, companies are kind of dependent on one or two individuals who are, usually scientists, right? Not IT support people to support these environments. So the idea that Certara can support this with their professional support organization and training, I think is something that'll, that should appeal to organizations that are looking to, have stable environments in R to work with. So I kind of touched on this already, but a fundamental theme is that the tools themselves generate code for you, either as the final product that you can directly work with, or as a starting point for something custom, tools that teach. So what I wanted to cover next was really just an overview of the job, right? We have the theory, we've learned a bit about R. Now, what is this job if you're sitting there and you need to do a pharmacometric analysis? What is that full job? And essentially the job, the way I look at it, and if you talk to analysts, they generally agree, it's from the data sources to the final deliverables. The final deliverables being generally either report, standardized data set deliverables, this type of thing. In other words, things that you would pass upstream in your company for further processing, whether it be into an NDA submission, that type of thing. But there's four main areas. Essentially, the first area is the setup of the analysis. Now, the very first step is taking your data sources, usually several data sources. Over time, these are progressing more towards standardized CDISC type data sets. I don't want to, if you don't know what that is, I don't want to get into it, but it's a industry standard kind of set of format and content for clinical data. And that's going to continue. But you take your source data sets and you format them into a analysis data set that tool like NLME can understand. And we'll take a look at that data set. And what you do is, after you have your first version of the data set, you do some data pre-processing. And here you QC your data set, you're checking for errors. You're also doing some exploratory analysis to try to figure out, okay, what's my starting model? Can I get a hint for some of the covariates that I might want to look at? This type of thing. So at the end of the setup stage, you should have an idea of your analysis methods, and you should be pretty confident that you have a clean data set. Next step is execution, where you'll take your analysis data set in your first method and you'll run your first model. And your first model, you fit your model to the data, and NLME will output a bunch of information. So these are, tables of predicted versus observed and individual parameter estimates and information about the run. And what you'll do is you'll take a look at this. You'll generate graphics that help you assess the quality of your thought, and then make a decision, okay, what am I going to do next? And you'll modify your starting model, make that change, run the model again, and repeat and rinse. So this is a very iterative process. A typical analysis can, take tens to hundreds of runs. And, again, management of these runs is something in the early days that had to be done manually. But, a tool like Piranha goes a great way to help users organize these hundreds of runs. And I'll talk about that in a bit. So you eventually get to a point where, you don't see any additional things to add to your model, and you're happy that you have a final model. And you say, okay, I have a good model. It's predictive. I think it's suitable for simulation. And you go into the next phase, which is either reporting or publishing of this analysis. But very often, these are interchangeable. In the end, you want to use this model. I mean, why do you develop the model? You want to use it to solve a problem or aid a decision. So, one example might be, you had some safety hint in your phase 3 trials that elderly females were more susceptible or had a higher incidence of AEs. So you might do a population PK analysis to look at exposures in, see if it's exposure related and come up with a dose recommendation if you do in fact see a relationship. However, that's one example. Another example where you might want to do some simulation is you did an analysis in your phase 2 trials, and now you want to design a trial such that 80% of your subjects exceed some threshold in exposure in order to really feel confident that the trial that you'll run in phase 3, the exposure will be sufficient there. So again, just a couple of different examples for why you do these types of analyses. And yeah, so reporting and publishing and simulation. So that's essentially the full workflow. Just to touch on, how users kind of work through this workflow. Now, historically, users, and I think this is still true today, right, like to select the best tool for the job. So the different fruits being different tools in this representation, right? So you might use one tool for data pre-processing, and then exploratory analysis, jump over to R. Execution, maybe, maybe you're using non-MEM or an open source NLME model, right? And this approach works very well, but, because for every step, you're picking a tool that does that job very well. However, it requires frequent tool changes, right? And okay, what's a tool change? It could be that you're working in non-MEM or a tool like that, and then you want to do some simulations in R. So what you have to do is you have to translate your model from non-MEM into R. And the model translation itself, might not be that difficult, but you need to make sure that the model is doing exactly what you think it's doing. So there's big QC overhead there that can complicate, tool changes. So, individually you have task efficiency, but collectively it's hard to be efficient. And where that really bites you is when you have these unplanned iterations, which are common. You might be at the stage of the report deliverable and, find something where you need to go back and, fix something in your data set and regenerate that. And when you're using several different tools, that can take quite a bit of time. In addition, if you go, this is the core pharmacometrics workflow, right? Most of us will be working for organizations where there's people we work with downstream, the data suppliers, as well as people we work with upstream, regulatory documentation experts. So to really have efficiency overall in a workflow like this, you need to consider up and downstream, business processes, and think about how can your processes help your business colleagues. And you'll see some of the stuff I show around what we're building for reporting tools kind of get to that point. Now, what the use of RsNLME, in other words, a tool that is based on the common thread of R enables, is a solution that helps individuals and organizations really work more efficiently. It's based on the same, PML model syntax. If someone develops a model in Win-on-Lin, that model now you can carry it all the way through NLME into R. And again, I mentioned, the support by Certara being an important feature. Now, what you see with the iterations, and just a very practical example, you may have prepared a PK report. Usually these end up as appendices and clinical study reports, and perhaps you used your company's drug ID number in your tables and figures, as well as the text of your report. And you submit it to your team and say, okay, here's the appendix, and the team comes back and says, well, the marketing guys want us to use the trade name in this report. And it sounds like a minor change, but if you spent, used a bunch of different tools to generate the different graphics, and within each one of those tools, you were using the drug ID number, and now your marketing guys want you to use a trade number, you're talking, it can be hours to days of work. And a tool like RsNLME would allow you to make that change in the code and essentially rerun your analysis. So major advance in efficiency. And earlier in my career, I used to look at guys who were proficient in tools like R and LaTeX, which is it's a publishing command line language, who could finish their analysis and have the report in a couple of days. And I would scratch my head and say, I want to do that. But the learning curve was very steep. And over years, I learned how to do it. That was also one of the drivers for why I wanted to build these tools the way we have, because the tools allow you to do some of this stuff without really necessarily knowing a whole lot about the code. But you can then take the code and learn for yourself. All right, how would I modify that? How would I actually do this? And I'm hoping that it really helps users who are, early in their career, perhaps struggling with command line, to become more proficient, faster than they would without these types of tools. Finally, I also wanted to mention that, RsNLME provides Certara an opportunity really to share open source solutions with the greater user community, so to participate in the growing community of data scientists who work in R. We have, again, I mentioned a couple of the packages, Tidy VPC. I'm going to show you our results UI, which again, that will be available in December. That'll be the next, the last lecture, I'll show that. And we're building other tools, and these tools don't just work with RsNLME. We're building these such that they can work with non-MEM and other tools as well. And if you're interested in taking a look at a recent webinar that kind of hit the nail on the head in terms of some of the drivers for why companies like us would be interested in working in open source, there was an interesting presentation in the RStudio webinars, where essentially, the point is industry-specific solutions. So solutions around pharmacometrics require industry contribution and collaboration. And yeah, again, we want to share, because we think the work that we're doing could be useful beyond, just within Certara. So in summary, R is hard, right? It's not an easy language to learn. I think you're getting a feel for that in this course, but the rewards are great in terms of unlimited flexibility, the efficiency with which you can do your work, and also access to a community that continuously improves. Every time you turn around, there's another great package coming out in metrics. So we hope to be able to do, we can't obviously have a Certara tool that as soon as another package comes out, we say, oh yeah, okay, we'll build that in, right? The idea was like, okay, we're going to work with these packages, and we're going to hopefully be able to point out, like I'm going to do today, some of the useful ones, so that if you decide to spend time on learning our packages, that Certara, we do a lot of pharmacometric work. Hopefully, it will come across, look, if this package is worth learning, you can take that to the bank, and your time will be well spent. There's over 18,000 R packages right now, I think. So yeah, it's overwhelming sometimes if you're just new to R and trying to do this type of work in R. RsNLME, makes it easy, not easy, easier. So it's designed to ease the transition to modeling in R And I talked about, we build Shiny apps that teach, and also Certara has the training resources to really help climb the learning curve. So what is Piranha? I kind of touched on this, and Piranha is a workbench for organization of pharmacometric modeling work. It's highly configurable, as some of you have learned in the installation. But once you get it configured, what it does is it ties together different pieces of software. And the configuration can be complicated because it's set up in a way to enable different combinations at different organizations, different users to be tied together. But it basically integrates various software tools, and it's a front end to RsNLME. It was originally built for non-mem, but we've modified it to work the same with RsNLME, and it organizes your model work. So things like standard, it provides a standardized file structure for run storage. It holds run summaries and diagnostics organized with a given run. It enables easy model comparisons. And again, I'll show some of this as we go through the course today. Provides a visual means for summarizing key analysis decisions, these visual run record reports, which I can show you. And from the organizational perspective, Piranha comes with a library of diagnostic scripts, but this is completely customizable. You can define your own organizational library of scripts to use with Piranha. So, the idea of harmonization around the use of open source tools is something that appeals to organizations. With free text open source tools, users are free to use them as they wish. They can type anything they want. They can use different variable names. They can take different approaches. With a tool like Piranha, you're able to say, all right, let's take best practices and build them into a library of scripts, and then generate, then distribute that to our organization. So if somebody leaves, it's easy for someone to come in and pick up. Piranha mostly supports the area that you see highlighted in yellow. However, we are building out, support for the expanded workflow. So again, I mentioned the reporting stuff we're working on. We're also working on a data QC Shiny application. Again, this will be available in December, and that's a tool that'll allow you to prepare summary tables from your source data set, study design specific diagnostics, that type of thing. So graphically, this is what Piranha does. You have a model, you submit it to an engine, and that engine dumps out output, right? The results of your fit. You see things like the theta values, residuals, bunch of information. What Piranha does is it takes this and organizes it. So each time you make a run in Piranha, it creates a folder, and all the results from that run will be contained in these standardly named folders. And within those, you have a key results summary, diagnostics, you can add analyst notes, and there's much more, but that's like a visual for what Piranha is doing. The second thing that Piranha is doing is, it's this front end to RsNLME. So it simplifies the interaction with the RsNLME command line. Within Piranha, you generally are working with what we call a meta model file. So those of you familiar with Phoenix tools will see this PML. That should look familiar. It is exactly the same language that you could run from within WinNonLin. And then the meta model file that you work with in Piranha is structured to be kind of like a control file, analogous to how you might work with non-mem. There's a data set designation, a map. This is where you're basically telling the model where the variables are in your data set, and then the model code, and you can provide estimation arguments to the engine and specify additional table outputs. Although unlike non-mem, the default table outputs from NLME generally are sufficient to support the types of diagnostics and things you want to do. And what Piranha does is it translates that into command line. And this is, just an example of what RsNLME command line looks like. You define a model. Here you're using an R function to do this. again, but we provide a GUI that I'll show you to do that. Set initial estimates, fixed effects, random effects, fit your model, and then run some diagnostics. There's much more on the command line and our vignettes that we're continuing to build out. You see a link here, and I won't open that right now because we'll take a look at that a bit later. Okay, so I wanted to pause at this point and just open up for questions around really the rationale for why we've built this tool the way we have. I think it's important, and yeah, I'd like any feedback or questions on this. I'm looking at chat. Silence. Does it make sense?
If anybody has questions that they would like to ask of Keith, please raise your hand. We'll be able to unmute you and you can ask the question. So I think Manish has a question. Manish, do I see that you have a question?
No, madam, sorry. I just put it in my hand on this resume. Sorry, I don't have it.
Okay, well, if there's no questions, I can go ahead and continue. Hopefully some of the situations that I described there really resonate with attendees, and yeah, I think I hope you'll like what you see. So where we will start then is on the exploratory data analysis. I don't know if you guys are getting blocked out from up here. So we're going to start here with essentially a raw data set, and we're going to learn how to use the Data Explorer within Piranha to check the data set for errors and also explore the data set. And then I'm going to show you how to take a bit more in-depth look at the data set using the GD Quick EDA. And again, I'm focusing on that because that's a graphical user interface for the ggplot2 package. And ggplot2, language, again, it can be complicated, but I think you'll like what you see when with the use of this tool. And the end result is we're going to decide on a starting PK model for our analysis. So just very briefly, I have an example data set here. It's called pkdata.csv. It's a 100 subject data set where subjects were administered 100 milligrams of drug X, right, intravenously at time 0, and then again at time 24. And blood samples were collected, serial blood samples over the first 24 hours, and then another sample at 12 and 24 hours after the second dose. The covariates in the data set include subject weight, age, creatinine clearance, gender, and a study center variable, 2 sites. So right now I'm going to jump out of my presentation mode here, if I can, and we're going to jump into Piranha. But first, what I want to show you is, right, within this directory that I'm going to, I just have a couple of data sets. I do have a homework folder where I, developed a homework assignment for the next session. But here in Piranha, you basically start with a data set. We can take a look at this data set. I think most of you should be familiar with a typical population type data set, but just very briefly, the way to look at these is as an event by event recreation of the dosing and sampling history within a given individual. So this first row or first event is a dose event where the subjects were administered, or subject 1 was administered 100 milligrams of drug X. These are their covariates. This data set, as well as many pharmacometric data sets, will have a, they'll use a baseline set of covariates, weight, creatinine clearance, age, and they collect that once at baseline, and then it doesn't change for the rest of the studies. If you have long-term studies where your covariates may be, important to either the pharmacokinetics of the drug or maybe a dynamic effect, then you would see these covariates change over time. You know, it varies. Most of the data sets that I've worked with, particularly the early ones, it's just a baseline covariate. But then the next event is a sampling event at 0.25. You have a drug concentration. And, you know, again, at time 24, there's another dose event. So that's the way you read things. The typical types of errors that come out of these are, you know, if you have reversal errors in date times, you know, when you calculate actual time, these will be wrong. But essentially, that's your typical PK data set. Now, what we'll do is we'll jump over to Piranha. And before I get into, so yeah, okay. So in Piranha, basically, you know, again, this folder is C Data Piranha Project D, Dontabhaktuni. I'm getting better at pronouncing it, but Project D is where we'll be working today. So I can navigate to Project D. One of the helpful features in Piranha is you can save this location. It says project name, save. And then now what I have is I can quickly navigate to that project. To give you an overall sense before I start here for what Piranha does and is, I'm going to just switch to a different project, okay? Now, this is a project where there's several executed runs. And what Piranha allows you to do, you see there's a summary table of all these runs. You see a quick, you know, what was the objective function? What was the improvement in the objective function? For each one of these runs, there's a set of files that are associated with that run. But more useful are these other tabs here where you see there's estimates. So for this run, these are my parameter estimates, my thetas, my omegas, my sigmas. Piranha allows you to very quickly compare runs. So if I hold down the control key and highlight 2 runs, I can go to results and show compare parameter estimates. And now I can see side-by-side views of the models. What else? The next big feature in Piranha would be the scripts library. And here, you know, for any one of these runs, there is a library of diagnostics where in Piranha you can just go and double click on one of these like I'm doing here. And what will happen is this will, you know, essentially generate your diagnostic plot very quickly. And when you do this, I'll just close that one out, close the current tab. A reports section is being created. So for run 2, my model 2 here, if I go here, all the diagnostics I've run for model 2 are kind of collected. Piranha also supports, you know, again, I mentioned like this visual run record. If I had an analysis where, you know, I did a bunch of runs, run 11 was my final model, Piranha gives you this nice way to basically create a graphic that traces the progress of your model out through the nodes. So here you see that green indicates a significant improvement in fit, red would be a worsening. I mean, in this example, they're all yellow. It's not really a good example to show this, but it gives you a feel for the visual run record. This is one of the favorite features actually amongst the consultants in Certara that use this, because you can put this in a report and it gives like a very clear, okay, this is my base model and this is how I got to my my final model. Kind of just to give you a feel for Piranha. You can, what else can I show very quickly? You can, for large analyses with many runs, you can, you know, color code models. So if I make 2 of these green, and why is that useful? Because then you can go to this filter and say, okay, show me the green models, right? And it limits it to the green models, right? Kind of useful stuff if you've been around the block a bit and have worked with large numbers of models. You know, this type of thing becomes very useful. So that's kind of a very, again, I'm trying to focus on the core functionality of Piranha. Of course, any of these models, you double click on them and up comes the code, you can edit them. There is functionality in here where you can actually duplicate a model. And so here the base model is duplicated. I added a weight covariate on volume. And then the Piranha will actually say, okay, because you duplicated the base model, I know that the reference model is the base, and I'm going to call this model 2. And then when I run these comparisons, I'm going to be subtracting the objective function of my new model from the reference model. So again, it just gives you a sense for some of the things that Piranha does. So I'm starting here with my with my blank project, and the first thing we're going to do is we're going to use one of the features in Piranha, the data inspector, to take a look at our data set. And I'm going to open a data set that has an error in it, just so I can show you, you know, some of the diagnostics that might catch a error. And again, this data inspector, it's very intuitive, right? You basically select your, you know, your X and Y variables, and Piranha gives you a very quick plot. So here I'm looking at time versus DV for all subjects. You can look at individual subjects if you hold the control key down. You can look at, you know, subjects, you know, alone or in collections. You can do things like zoom in, right? If you click outside, it'll zoom back out. Very quick way to look at your data set. Here we have these additional doses, right? If I'm trying to, maybe I'm trying to decide the structural model here. So I want to look at log scale. Maybe I don't like these, right? I just want to look at single dose over day 1. So I can maybe filter, you know, say I want to look at time less than 25 hours. Okay, that looks all right. I also have in my data set, recall that my amount rows, right? My dose rows, I have a 0 there for my dependent variable. Maybe I don't want to see those in this plot because I'm trying to just look at the concentration data. So if I type amount equal to 0, right, and filter on that, it removes that, you know, that those dose record plots. So now, okay, I have kind of a feel for this. Is it 1 compartment? Yeah, maybe 2 compartment. I'll probably start with a 2 compartment model here. So that's one, you know, one way you can use the data explorer. Another quick QC of the data set would be these what I used to call index plots. So you're basically using ID on your x-axis and then just stepping through the variables on your y-axis. Maybe I'll remove the log axis, right? So ID to ID, okay, that's directly correlated, of course. Here, I would be looking for any errant time values. So it looks like all the IDs have, you know, similar times. This data set, it's really just nominal time. It's not actual time. DV, are there any like major outlier DVs? Nah, this looks all right, right? Amount, dose amount, everyone got the same dose in this trial. Weight, right? Weight, okay. So this is an example of an index plot that would immediately show, hey, there's an issue here. So I know in my data set, all my weights are clustered down here except for this one guy, you know, at 500 kilos. So at that point, you might want to go back to your data managers and say, hey, wait a minute, you know, we have a trouble with this data set. Creatinine clearance, age, I think you get the idea. I mean, you can also do things like, you know, check your dependent variable. Sorry about that. You know, against ID. Again, you're just looking for patterns. And here, weight, well, you know, this is getting kind of screwed up by this 500 kilogram. You know, at this point, you throw your hands up and you say, how am I supposed to work this way with this dirty data? And you get back to your data managers and they send you a clean data set. So if I open this data set, you know, it's the same data set. I just fixed that weight. So we'll reopen this in the data inspector. And I was looking at just DV versus covariates. So yeah, I mean, it's a very gross way to look at this type of data. And I'll show you how to refine that within ggplot. But here, you know, okay, is there, maybe I'll flip this around, weight DV, right? Is, you know, this is, again, looking at all samples, but lower weight patients seem to have higher DVs in general. So again, it's a hint, maybe weight, you know, could be an important, you know, covariate in my model. Creatinine Creatinine clearance, same thing. Well, that's going to be correlated with weight, but again, you might see a pattern here. Age, nah, nothing really there. Gender, yeah, possibly. So just gives you a sense for some of the types of things that you can do with the data inspector. Now, the final thing that I wanted to mention about the data inspectors, you see this block down here. So what this block down here is doing is it's providing you with the R code should you want to recreate this plot within R. And it gives you 3 flavors. So there's like base R, there's something called the lattice package, which was a graphics package that's actually quite useful. It predated ggplot and of course ggplot2. So if you were to basically click on the R button, this would open an R, and you could regenerate this plot within the within your R environment. Just one point to notice: before you've created any models, the working directory, Piranha can't pick up where the working directory is. So if I were to import this into R, I would have to make sure to set my working directory to this Piranha Project D folder, and then the code would run. After I have my first model in here, you'll see Piranha then is able to populate this working directory. That's in this version. It's going to be corrected for the December release. So that is the Data Explorer. Now, what I wanted to do next, before we jump into developing a model for that, is again this quick introduction to ggQuickEDA, which is something again, this is a package that was developed by one of our consultants. It's been around for quite a while, but I think it is a very, very useful package and worth your time to learn, because you can do incredible things with it, but it also can help you learn ggplot. So I have a script here I prepared, which I can make this available. Don't look at that part. That part is actually is what is returned from the app, and I'll show you how that works. But it's up here. So what we're going to do is we're going to load this library, ggQuickEDA. We didn't talk about this in the installation, but to get this, it would simply be tools, install packages, and then you would be able to just type in ggQuickEDA here and hit install. That's how you would install this package into R. And then what I'm going to do is set my working directory to Project D. So again, that points R to say, okay, this is the area that I'm going to be working in. There's an easy way to do that, right? If you forget the set working directory command, you can basically go to your file area and you can navigate to this. So I'm C data R RsNLME, C data R RsNLME. Sorry, I went one too far. And then training, Project D, and under more, you have set as working directory. And if you click on that, you see down here in the code, it says set working directory, right, to Project D. So there's a couple of nice features in the RStudio that you'll learn over time that allow you to do things if you forget. Next thing I'm going to do is I'm going to use the read CSV command to read in my PK data CSV file. So I'm going to go my data read CSV. So now I have a data set in my R session. We can take a look at it. Yeah, it's our data set. And then I'm going to run ggQuickEDA. So here I'll run this. And it's loading package dependencies. Many packages in R depend on other packages in R. So when you load them, they'll go and they'll load up what's required. But here the interface is launching now. Hopefully it'll be speed okay. A little bit slower, I think, because I'm on a Zoom meeting. So it's uploaded my data set. and now it's going to give me my menu. And essentially my Y variable, I can look at DV versus time, and my plot should come up, I hope. I don't know if this is going slow because of the Zoom meeting. I think once it loads, it'll be okay. Time. There we go. Okay, so that indeed looks like our data set. Now the things that you can do, again, this can all be done from the command line in ggplot, but the interface makes it very easy. So perhaps what I want to do is, make my points a little bit bigger. Maybe I want to add a line. So if I add lines, that's not the kind of line I want, right? I might want a line by subject. So here I go and group by ID. And then, okay, that looks a bit more. I can go back to lines. Perhaps I want to make those lines a bit smaller, maybe make them transparent. Okay, so that's giving me a nice spread of data. Now, let's see. I can go ahead and change the y-axis to log if I want. Again, I'm trying to get a feel for, the shape of the curve. Maybe I want to get rid of the 24 and 36 hours again. So here in ggplot, you have a filter capability. So if I filter time, and then it'll bring up a window of times. Okay, what do you want to show? If I hit shift and go on 24, it just selects everything up to 24. That looks pretty good. I still have this line coming down from 0. Now I know from my data set, there's no 0 DVs. Those are actually the amount records. So maybe what I also want to do is take my amount and filter that to the 0 records. That should come up. So that's looking a little bit better. All right. So next thing I might want to do, and one of the very powerful features in ggplot is the capability to lattice and kind of cut data sets into categories for visualization. The ggQuickEDA makes this very easy to do. It's easy to do in ggplot if you know the code. Here, you basically can just say, okay, I want to split the column. Maybe I'll try to blow this up a little bit. Sorry, keeps going down the here. I'm going to do a column split by gender. Right, so now I have a plot by gender, and here these are my males, these are my females. So right away, I might say, all right, maybe females do have a little bit higher Cmax value here. There might be something going on here. I can add a smooth to this if I want, right? Smooth and standard error. All right, I hope you're getting a sense for, the flexibility of this interface. Going back to groups now, maybe I also want to look at, weight. Weight was another possible covariate that we saw in those previous plots. So if I click on weight here, it's gonna, generate a plot. Hopefully it'll do it fairly quickly. Now I'm doing that to intentionally show something bad. Now, what happened here? Okay, when you split by row and you use a continuous variable, it's trying to treat each weight number as a separate category, and that's not what we want, because this is nonsense, right? You can't make any sense out of this. So if we remove this, if we remove that, I want to show you another feature within ggQuickEDA that's very useful. And essentially, if you go to categorize cut, what you can do is you can take a continuous variable like weight and very easily cut it into categories. Here, I'm just going to use quantiles. So maybe I'll say 4 quantiles. And what ggplot will do is cut this plot into quantiles such that now, if I go and maybe this time I'll split column by weight, and then I will add a row for gender. you see now I have a, maybe, okay, it undid my filters. It will do that when you recategorize variables, but I can very quickly correct that. Again, just by going to my filter time and head down to here, shift, and then filter my amount. Again, my amount to 0. Okay. All right. So yeah, now I have an interesting plot. You can see here a trend for the females. The lowest quartile of weight, 34 to 49, maybe has higher exposures, kind of drops as you go left to right. There's not a lot of subjects here. You kind of see a general trend, maybe not so much in males. So this might be a plot that you want to put in a report somewhere. So you can either, directly export this plot. However, what ggplot, ggQuickEDA enables you to do is, sorry, it's coming up on my, it enables you to basically copy the code that will work at the R command line to reproduce that plot. And the way that ggplot works is that the instructions are right here to reproduce a plot in the data tab, right? Show all rows and save the plot data into a CSV. Now, why do you need to save the data set? Well, when you do things like categorize and cut, what ggQuickEDA is doing is it's creating additional variables in the background to enable those plots of the quantiles of weight, for example. So if you go to data, and it'll show the data, you show 5 rows, right? Show all rows and hit download. You can then download this data set that was used to generate the plot that we saw, earlier. And then I could take and copy this code, just essentially copy and paste. I'm going to close this now. There's other things in here that are kind of useful, but I encourage you to take a look at it. I'm only scratching the surface. So here, this is my return plot from ggQuickEDA, just paste it here. And then what you can do is, execute that, have that in R script with your data set and be able to regenerate the plot that you had. There it is. So again, a GUI that allows you to do, again, ggQuickEDA is a great exploratory data analysis tool, and it'll really help you learn the R code. This R code looks very complicated. My only recommendation would be that, don't get a lot of the code that is returned by tools like ggQuickEDA is generalized. So you see this input $, input $, input $. All those are doing is storing selections that you made in the GUI. And then where the real guts of this is and where the learnings are is down where you see called the ggplot. So you see ggplot, your data object, your AE strings, this is your X and Y variables, and then all of the geomes that are used to generate that plot. And you can easily go in, and just modify some of these. Backgrounds white, right? If you change that to red, right? And then re-execute that plot of code, right? It's easy to, again, it's a starting point. You can further customize. Of course, I'd never put that in a report, but that gives you a sense for ggQuickEDA. So maybe I'll pause there for a second. Any questions coming up, or if not, I can minimize that and then go into the next step, which is specifying the and executing models. So just pause very briefly. I hope that was useful. And again,
thank you.
Yeah, sorry, go ahead.
No, thank you, Keith. I think I'm also looking at that the participants will be working through what you are showing today as they're working through the homework assignments. And that's when they are doing the work hands-on, that's when they would really understand what RsNLME is all about, and that's when they would have real questions. As of now, they're just getting this as a concept.
Okay,
And
great.
For all of you, I also want to mention that I am new to RsNLME as well, so I would be working through the homework assignments similar to what you are working on. So, I can see where Keith is, and that as you're working through that homework assignment, you would really know the utility of the tool. And that's when the real questions will come up.
Yep, and we're here to help. Again, feel free to send me an email during the course and even after. Very interested in helping people become more proficient with our tools and in general. So again, I wanted to show GG Quick EDA because it is an excellent example of one of these packages that exists out there in the R universe that is just incredible. And if you don't know about it and have never used it, you don't even know it's there. So again, in the work that Certara consultants do with pharmacometric consulting, we have over 250 PhD level consultants. These are the types of tools that we're using. So I hope it's helpful. So in this next section, we have an hour left, right? I'm going to basically show you how to specify a model using the Model Builder Shiny app. I showed some examples of PML. You don't have to know that language. The GUI will build these models for you. Of course, it helps to understand the syntax. Anna's going to spend some time talking about, just a brief introduction. So you're going to build a model. We're going to fit that model in Piranha, and then we're going to take a look at the model results and look at how to customize default diagnostics in R. And that'll wrap up for today. So I'll spend just a bit of time going over the homework, but essentially the homework steps you through what I've covered today in the lecture series. So yeah, okay, we don't need that. So we're going to go back to Piranha now. And right now I just have my data sets. Okay, so what we want to do is we want to, again, we want to start with a 2-compartment IV model. And in Piranha, we have this models section. And what we want to do is we're going to execute a new model. Now, I mentioned, I just want to point this out. Piranha works with non-MEM and RsNLME. The way you tell Piranha which tool you're working with is through this button right here. So there's the MMDL, which is the meta model, or that's the NLME function. There's also in my configuration mod. So mod is the extension that I specified in my settings that'll work with non-MEM files. So make sure that you have the MMDL selected for this course when you're working in Piranha. Now I'm going to create a model. So here we'll go to models, new model. And for this example, I'm going to use the model builder. We do have template-based models, but it's, I mean, I think you'll be using the model builder. It's just so much easier and better until you become more advanced, and maybe you can start from templates when you're working on custom models. You would navigate, make sure you navigate to select the data set that you want to work with. And then you essentially run the model builder. Now, what this is doing is it's launching the RShiny app, which is the model builder app. This model builder app can also be launched from the R command line if you're working outside of Piranha. It's the same interface, but here we're launching it from within Piranha. And this is what the interface looks like. So it's very intuitive, and the way we've designed it is such that when you make selections for the types of models that you want, the code is generated immediately for you and shows in this window here. You can always look at your data set if you need to pop over and take a look. And I'll show you like when that might be useful when you're specifying covariates, for example. But this interface supports, I don't know, I counted one time over 100 types of models that are built into RsNLME. And just to give you a very quick sense, right? If you want an indirect response model with 3 compartments and Michaelis-Menten elimination with first order absorption, right? You see this code building as you select this stuff. Maybe you want an additive model for your effect observed, but a multiplicative for your C observed. Here, the tool is building the PML code for you immediately. So you don't have to know PML. As you get to learn PML, the syntax will begin to make more sense to you. There's a dose point into absorption compartment here. Here's your differential equations. The sequence call is how you define a variable in PML. I don't want to get too far into the weeds. Again, Anna is going to give a an overview of this language, but you don't need to know how to write it because this interface basically writes the code for you. In addition, we won't be using it today, but if you make selections in the interface, you can generate the command line code here. And if I'm not going to do it, but if I were to hit generate here, it would give me RsNLME command line code that I could copy into my R session to essentially start with this modeling work. So again, it's that repeating, recurring theme of the tool being able to teach you how to do this type of work. So we're going to get away from the indirect response model. We're going to go back to linear clearance. We'll select 2 compartments. So we have a PK model. Our absorption is IV. Under options, there's a couple of things. The most important one probably is if you have infusion information in your data set, you'd want to, there you need to have a rate column in your data set that says the infusion rate. But what I wanted to show was really the closed form. So closed form models in RsNLME they're not written in the form of differential equations. They're just written in equations. So when you see like CF micro, that's saying, okay, there's a model here for a 2-compartment IV PK model. These generally run faster than models written in the form of differential equations, but you can easily swap back and forth. PML supports both. And again, if you want to swap from one to another for a built-in model, it's as simple as clicking that. If you need an example for how to do this, if you're writing your own model code, open the model builder and just make some selections, and you can see how to proceed. So we specified the structural the structural part. We're going to start with maybe I'll pick an additive model, even though I know it's a wrong model. And I think we'll take a look at the conditional weighted residual curves in the diagnostics, and we'll see like an indication of why that's not a good model, just for the purposes of the course. So I've selected my main base model, my residual error model, and now I will click on next. And this brings up the next interface that you step through, where I specify what structural form I want my model in. So here it's like the parameter times exp eta. If you note here, there's also sum times exp eta, right? What these are doing, it's basically telling the model how you're going to want your covariates stacked when you begin to add them to the model. But suffice it to say, by default, it takes the parameter and then it exponentiates the eta. So this is like a common, most common eta specification for doing this type of work. You can select which parameters you want your eta terms to stay on. Here, I'm going to remove it from B2 and CL2. You see the code immediately updates. I'm going to add some covariates to my model. So this tab, you don't hit next, you step through the kind of the headers here. And if I click on the plus, now I might say, okay, what covariates do I have? If I, excuse me, go back to my data set, I have weight, crayon clearance, age, gender, and a center variable. So here, you know, I will, you can either type it in. Because I've worked with this data set before, it populates it for me. The first time you do this, you may have to type it in. But I'll go to weight. Let me just go back to the PML so you can see this. And weight is a continuous variable. You have the capability to add continuous, categorical, or occasion covariates, like Serge discussed in his earlier lectures. I'm not going to mess with occasion variables in my coursework. Again, I want to focus on just the core simple PK, so you can get a feel for how the tools work. So we have a weight, continuous, and you can center on variables. So you see the you don't see it yet because I haven't specified on what I want to put this covariate on. But if I were to select volume, which I wouldn't generally do for a base model. For a base model, I want to add my covariates, but I don't want them actually calculated on any parameters. Rather, I'm adding them so they're available for my diagnostic plots. And I'll show you that later. But so weight type continuous, I can center on the mean value. So what it's doing is it's taking my volume is going to be my typical volume times weight over my mean weight raised to a value, and this is what is going to be fit, you know, when I run the covariate model for this. You can center on mean, you can also center on median, or you can enter a value. Maybe I'll enter a value of 70. So that's weight. I'll remove this from volume. Again, I just did that to show you. What this does is it pops this F covariate weight and then creates a space for that to be mapped in your data set. And then it becomes available. You can do things like clearance versus weight in your diagnostic plots. So I'll just repeat this for, whoops, did too many. I'll do age. See here, it's not populating age, so I'll type in age. This is continuous. Maybe I'll center that on 35. I will add another one. Let's do, what was it, crayon and clearance, CRCL, continuous. Maybe I'll let that center on the mean. And then let's do a gender. And then gender is categorical. You can see this is all quite intuitive. Now in my data set, levels are 0 and 1, 0, 1, and then my labels might be male, female. All right. And again, if you wanted to see, like, okay, how is it coding a categorical covariate? You know, you might just pop it here and take a look at this. So this here actually for categorical, where it's, you know, you have a 0 or 1, what this is doing is it's a logical check. So in your data set, if sex equals 1, the return of this would be a 1. So it would be TVV times EXP DV sex V1. Now, if sex equals 0 in my data set, this sex equals 1 would return a 0. And then this times 0 is 0, anything raised to 0 is 1, so it drops out of the equation. So that's the way that, okay, my volume estimate would be my reference volume estimate, and then the DVD sex 1 would be a scale factor for females in my example. We could talk a bit about that more if I just lost people. But, you know, a lot of these population PK models, you need to follow the math in terms of how they've been coded. And this holds for non-MEM, Expo, you know, RxODE, any of the open source packages, including NLME. Maybe I'm going off on a tangent there, but all right. So now we have some covariates in the model. I want to next go to my fixed effects. So these are my initial parameter estimates. I'll just do 100 and, you know, know what these are. I should have an idea from maybe NCA or, what these parameters should be. There is a feature in Piranha that allows you to check your initial estimates that we'll take a look at. And then finally, my random effects. Now this says, okay, you have an A to V and CL. Do you want to use both of them? Yes, I do. And here's where you could specify, block omega matrices, this type of thing, by simply unchecking diagonal. So if you have correlation between your etas, here's where you would, specify an initial estimate and have that. So we'll just stick with diagonal. And we're going to start with a 0.1 here, 0.1. Okay, now I can go to next. Now I don't have steady state dose columns in my data set or additional dose columns. These are ways to, indicate in your data set, if you have longer term studies, that type of thing. My study is very simple. We have 2 doses and both are explicitly, included in the data set. So we won't be using that. The next button then takes you to the column mapping. So what is this column mapping? Essentially, I have a slide for this because it's quite straightforward, but seems to confuse a lot of new users. When we talk about column mapping in RsNLME, this is what we're talking about. So you have, essentially it connects your data set to your model. So you have a model that you specified, and that model expects certain variables, right? The ones in red are required. In other words, the model won't run without them. The ones in green, in this case, covariates, are optional. So the mapping process is essentially saying, okay, model, the variable that you know as ID is actually capital ID in my data set. Time is time, A1 is amount, COBS is DV, weight is weight, sex is sex, et cetera, et cetera. There's many others too, like I mentioned, steady state dose information, that type of thing. So that's essentially the mapping process. One of the interesting things about NLME versus a tool like non-mem is that NLME is a lot more flexible with how your data set names are named and how you can map those to like different names within your model. And it's like good and bad. It's good because the flexibility is there. You don't have to be so strict with how you create your data set. But it's bad because it can create some confusion, especially if some people have, learned a little bit about non-mem where, the data set structure is very, very standardized. But yeah, I just wanted to, show what mapping was. Now we can jump back to the mapping field. And again, it's intuitive. ID is ID. My time is time. COBS is DV. So again, COBS is the observed concentration that the model is expecting. We're saying, okay, that's DV in the data set. Weight, age, creatinine clearance, gender, and then A1 is my dose or amount in my data set. Now, here's at the point where I could actually generate this code. I'll go ahead and do that just to show you. Takes a bit because it's taking the the GUI inputs and putting it into code, and there it is. So here's your model. It's a PK model command. Now this is more verbose than it needs to be because the GUI actually returns all of the options within the script, whereas many of these are default and you wouldn't have to specify them at the R command line. But this could be copied right into the R command line and run. But what we're going to do is hit save and exit. And what this will do is we'll go back to Piranha. Now, another thing about Piranha, this little green refresh arrow, you'll be hitting that a lot. Piranha is written in a language called Perl. And Perl is, it's an appropriate language because originally it was designed, again, Piranha was developed for non-mem. And Perl is a language that allows you to parse a lot of text. So you can pick pieces of text out of model export runs and organize it and do different things with it. However, the GUI functionality of Perl is a bit antiquated. And, you know, this is why you need to hit the refresh a lot, because that object was there, but you don't see it until you hit the refresh key. So if you're not seeing something that you think you should be in Piranha, click on the refresh button. And what we have now is our model. So if we double click on this model, this is the MMDL file that we just created. So we have a 2-compartment model, right? Our initial estimates there, our random effects, you get the idea. We specified our covariates. Our mappings are done here. And we can actually add a description, maybe say base model. Right, just save this. Now, Notepad Plus is the editor that comes up for me because that's what I set as my default in the Piranha settings. So yours might look a little different depending on what you picked. So if I hit refresh, now my description comes up, and I have my my PK model. So just to make sure I'm covering everything. Okay, now what I want to do now is turn it over to Anna, and Anna is going to give a overview of PML language.
Thank you very much, Keith.
Do you want to
All
share, or
right.
do you want me to advance the slides for you?
I'll go ahead and share on my end.
Okay.
Okay, just hold on 1 minute. Let me know if you can see it on your end, please.
Yes.
All right, great. So we're going to take a step back now and talk about PML. So PML is our pharmacometrics modeling language. And I have to say that we got kind of lucky because prior to that, we used to call it the Phoenix model language. So if any of you are familiar with Phoenix, it is the same exact syntax. So as Dr. Nieforth showed you, all these amazing wizards, all these RShiny apps write the code for you. However, it does that for the library models, and there's a lot of library models, but they might be when you start doing more complicated models, the need for you to modify that PML. Okay, so we wanted to give you a basic introduction. This is, of course, not everything that you would need to know, but just to give you a little bit of an idea on our PML. So PML is case sensitive. That's the first point that I wanted to make, because if you have an uppercase somewhere and a lowercase, is going to look at it differently. So it is case sensitive, so be careful with that. Most of the time, the order of the statements that you write does not matter. So you can have, I think you saw some of those derivative statements. You can have it in the beginning, you can have it at the end of your code. It doesn't really matter, except if it's within a sequence type of block, and we'll talk about that. So the order in general doesn't matter unless you want it to matter, and then you put it within a sequence block. The statements can also span multiple lines. So it doesn't matter if you put a return or not, they can span through them. There's only one exception, and it's with comments. So with comments, if you want to comment your code, you can use kind of like the pound sign, and that would go to the end of the line. So if you put a return, then after that is not considered a comment anymore. Now, if you want to go multiple line, you can use kind of like the same as SAS. If any of you are familiar with that, that would be slash, the star, and then your comment will continue until you close it again with a star and a dash, right? And there's another way of commenting, which is the 2 dashes, the 2, I guess it's called backslash. It goes to the end of the line. So those just comment the code if you can put whatever you want in it. Also to mention that the variable names cannot contain a period, so you wouldn't be putting a typical value of volume, like a typical V period and then a V. That wouldn't work, but you can use an underscore, or you cannot use anything, just TBV, right? So just to point that out. And also within the values of your columns, they cannot contain commas. So this is important, especially if you are in Europe, with some of the values sometimes are presented as a comma. You need to be very careful with that. And I'm not going to go through the whole list, but PML has some reserved words, like for example, model or block, etc. So sometimes you may run into issues if you're trying to use a reserved word. And I'll point you to the guidance where all those are specified. All right, so we're starting with these. Let me just close. Okay, so we're starting with PML. You will have this starting model name, okay, and that's followed by these open and close parentheses. Now, this name test is what our wizards and those RShiny apps put in there, but it could be something called my model or run one or run two, whenever it is. These can be changed, but you will, most of the time, if you're using the wizards, you will see this test. And don't worry too much about the parentheses. Those were used to pass arguments if you wanted to run things in batch mode. But in general, they would be empty like that when you're using RsNLME. Okay, so we're defining in this case a model that is named test. And then that is followed by the PML code, and the PML code needs to be embedded within curly brackets. Okay, so these curly brackets identify some type of block within your code. In this example, I have here like the structural model statements, just to start showing you some of those. And for example, deriv is the differential equation. Okay, and it has them in terms of amount. So these big A's are amount. So you can see here, this is a one compartment model with extravascular absorption. So we need an absorption compartment. So it has a derivative for that. And in our case here for the dose point, this identifies where the drug will be input. So it goes into the absorption compartment. But an example that I have put here, if it said dose point A1, that would be that you're dosing in your central compartment in the case of, for example, IV. But because everything is in terms of amounts, but what we are observing are really concentrations, then the code requires that we do the transformation. So that means that the C, this concentration, is equal to the amount divided by the volume of that compartment. All right, so these are some of the statements for the structural model that you will become familiar. And I wanted to mention that the dose point statement can have several things within it, okay? So yes, it specifies the compartment that can receive a dose, but the syntax within the parentheses is not just the compartment name like we have here, but you can also use a TLAC, you can have duration, you can have a rate, and you can even specify bioavailability. So the way to do this, probably better to look at an example. If you want to specify a TLAC, you can say TLAC equals, and you could put a number if you want it to not be a parameter to for the model to really estimate. I'm sorry about that. But if you wanted to have a parameter called TLAC, you just say equal to whatever name you want to give it. Okay. And then later on, I'll talk about the structural parameter statement. Here it is, you can give it an expression to. In this case, there's no between subject variability. So the typical value will be the same. And that one then can have an initial value. So we'll talk about those coming up. But my point here was to, within the dose point statement, you have that compartment name where the dose is receiving that dose, but you can also specify things like TLAC. And you can also specify bioavailability by using this bioavail statement and then an expression. In our case, an expression is to say, I want to estimate it, and the name is going to be F. Okay? So that is a little bit more on dose point. Then we have some statements for the error model selection. The most important here is the observe statement. So the way that you would read this defines your residual error model, is to say that whatever I'm observing, my concentration in my file is going to be equal to whatever the model right here, the C, is estimating plus some error. So this is noise in your model. And the way that this is written is as an additive error model. So it's just a plus these CFs. And then on top here, this error defines the initial condition of the error, standard deviation. So CFs is going to be equal to maybe 1. That really depends. It depends on the magnitude of that of your concentrations, right? But you could also write it as a multiplicative. So that would be C plus 1 plus CFs. Okay, so that would be the multiplicative. And this one is missing a parenthesis in here to close this observe statement. So you can play with that when you go into the RShiny, the model builder that Dr. Nieforth just showed you, and you can play into selecting additive or mix plus additive, and you will see how these observed statements change. All right. Also keep in mind that this is a standard deviation within this the error statement. For the parameter model selection, you can see that we have different statements here, the ST Pharm, which is the structural parameter, and this fixed effect. Okay, in this example, this is not a population model. There's no between subject variability here. So there's no ADAS. And you can see that it's all these statements are saying is that this KA is going to be called the typical value of KA. Okay? So there's really no there's no between subject variability, and we're studying a little bit easy. I'll show you in the next slide a population model. But the statements here, this defines the structural parameters, so this can have more things to it. And here is where we put the ADAs, where we put the covariates, and what you're probably going to be looking in your PML code to see how you're entering those covariates into the model. And then the fixed statement is used to identify the initial values and maybe some bounds if you want that. We don't recommend using bounds to start with, but in some cases, if your estimates are going to negative, you may want to put maybe like a lower bound of 0. And the way this works is it has this C indicating this vector, then a parenthesis, and here it would be your lower bound and comma, and the center is the initial estimate, comma, and then in this space, it would be your upper bound. Okay? So if you have a statement like I'm showing you here, with a fixed effect of clearance, and it has this C, 0, 10, 100, it means that I want to start as an initial estimate of 10, but my lower bound is 0 and my upper bound is 100. So I don't want that estimate to go lower than 0 or higher than 100. The engine usually doesn't like to be that constricted because it's bouncing all over the place, and it prefers to be kind of left alone and come back to that estimate. But if it's for some reason, as I mentioned, this is going to then ultimately give you a negative clearance, then you may want to put a lower bound of 0. And after that, we also have this random effect statement. This is randf. And this is specified if you have the random effect parameters and the covariate structure. So how does it work? It has this randf, and then you would see in these parentheses, you may have a diagonal or you may have a block with those ADAs. So I think it's better if I show you an example with some of the wizards that we saw. So when you go to the random effects tab and you select some of those random effects right here, there is a matrix that opens up. Now, if you put a diagonal, you won't see these zeros. It would just be the diagonal of the matrix, and that would indicate that they're independent. Okay, so if you want to have them independent and no type of correlation between them, you put you click diagonal, and then you have you can enter those initial values in the diagonal matrix. This would look, if you have a diagonal only, it looks like this. It has diag, the name, all your terms in there, and then the initial estimates and in this C vector. Now, if you don't check diagonal, what you will see is the word block. That means we're doing a full block in this case. The terms within that, and then this vector C is read as follows. It's read, kind of think of it as a row. Okay, so it says, okay, so the estimate for this random effect for Ka is going to start at 0.2. Then I'm going to start assuming that I'm going to start no correlations or 0, and then let the program estimate if there's 1. So that's typically we enter zeros. And then for MV, the initial estimate, it's going to be 0.2. So this is how you read them. So it's 0.2, 0, 0.2, 0, 0, 0.2. So by rows. And this is how it's entered in the code. Okay, so that's a block, meaning that we are estimating these covariances. Now, if you want to split things, if you want to, for example, between Ka and Cl2 to not just be a diagonal, you can do that. You can split them, indicate diagonal, and you will see in the statement that this is RANDEF diagonal for these two terms with the initial condition. Oh, sorry, I keep going to the other one. But for the other ones, for the V and CL, I wanted to have a full matrix, so I hadn't checked diagonal, and the code there will call it a block, NV and NCL with the initial conditions, okay? So again, this is red 0.2 as my initial estimate, and then 0 for the correlation and 0.2 for the CL. So I hope that makes sense on how the code in PML is translated. Now, we did see also covariates, so I wanted to talk briefly about this. And there's 4 ways of having the covariate code. The F covariate is the one that is the default and you're going to see most often. So that specifies that you have a covariate, and the name will go here in the parentheses, and that this extrapolates forward. And what does that mean? And I put some examples here. It means that the engine needs to have a covariate value every time that it evaluates it. So if you had maybe a covariate at time 1 and 2 and 3 that had these values 10, 20, and 30 respectively, the F covariate basically would say that between 1 and 2 it's 10, and for 2 to 3 is 20. And then any time beyond 3, it's 30. So it goes forward, okay? But if no covariate is specified at time 0, then the F covariate does use the first time. So it would use 10. So it's taking any covariate value that you have and move it forward, okay? So if you didn't have at a time, let's say you wanted a time 2 and you didn't have anything there, it would take the previous covariate value. So those are for time-varying covariates. Now, if the statement is just covariate, this specifies that you want to extrapolate backwards. Okay? And the example for this is similar as before. Let's say you have a time 1, 2, and 3 with these covariate values 10, 20, and 30. Then this would be from 0 to 1, it was going to be 10. Okay. From 1 to 2 is 20. And from 2 to 3 is going to be 30. Right? So we're going backwards in this case. So that's just the code. F covariate forward with no F, it means backwards extrapolation. Now, if you had something that is not continuous, that is categorical, then there's an extra parenthesis here. So as you can see in this example, this is F covariate, but then it's gender, which is categorical, with these parentheses and then another parenthesis that closes this statement. And so these are some examples of a gender or smoker or race. That is the way that the PML writes these. And of course, it could be F covariate or it could be covariate. There is another way of indicating a covariate, which is interpolate. We don't use that as often because it can cause, in some cases, it can really difficult converging. So just be careful using that. But basically, these interpolates between the values of the covariates, and it uses a linear between the time points to come up with the value of that covariate maybe. Okay, so this is the different, in PML, you have F covariate, you have covariate, and then a different way if it's a categorical by adding these extra parentheses. Okay, you will see also that within the fixed statement, we have this enable, and those are useful for covariates. If you're going to be doing things like, we have the options to have covariate search, that we haven't showed you yet, but it's going to be some options of the engine to determine are these covariates maybe significant, are they important, and you can do this selection of covariate search, and enable means that it's going to allow those to be in your model. Okay, so they're going to be part of those covariate search or stepwise, or in some cases you can also do just scenarios of your trying to identify if that covariate is significant. All right, so we're going to this fixed statement, and as I mentioned, is that enable. There's also a way of putting the initial condition here. So this C, as we saw before, is the initial condition within the fixed effect. Some examples: if you only type a number, it would just assume that's the initial value. If you put it within this vector C, this is the lower bound, the initial value, and the upper bound. Or if instead of just typing the value, you put it within the C vector, it's the same. It just indicates the initial value for, in this case, clearance is 0.03. If you have the word freeze, which in the wizard or the RShiny app, you also saw that you can put a checkbox there. It just fixes the value during the full estimation process. And if you have that enabled, it enables that covariate to be part of that covariate assessment. Okay, so we have, and I don't know if we're going to show it, but there's a covariate search stepwise as well as a shotgun options within the tool. All right, other commonly used PML syntax that you might need to identify a new parameter. So you can use double. Double is kind of an old statement for Fortran. It just means double precision. You can use double. You can also use real, and that will allow you to put in your code a new parameter. We have this sequence block. And this is the only place, as I mentioned before, that time does matter. So it is it's processed at certain times. So that's unlike the rest of the code. It can be used to define initial conditions of your ordinary differential equation. So if you type like an example here, this effect is equal to some type of baseline effect, you can do that in the sequence statement. Or you can have other expressions. So one that is very useful is the sleep statement, because it is instructing the engine to kind of sleep for an amount of time. So an example here would be like if I write something like a sequence statement, I use the statement while my time is less or equal than 10, I would like to sleep for 3 time units and then wake up and have my amount equals this initial amount in the absorption compartment plus some other dose amount. So you could do things like this by using the sequence with maybe a while statement. So this is a lot of information that I'm giving you. As mentioned, most of the code for all the library models is going to be written for you, but at some point, if you get into more complex models, you will need to write that PML. So what we recommend is to start with the library models, get the PML code, and then modify it with the statements that you need. If you want to learn more about it, I have a reference here of the modeling language reference. Now, this was written for Phoenix, but as I mentioned before, it is the same language. So you can go to this reference and you can learn more about PML. As part of this course, I also thought it would be interesting for some of you, if you want to learn more about PML, to take this course, which is this Getting Started Learning PML Code, and there's some videos that are associated with that. If you're interested in doing this, go to Certara University, find this course, and then at the checkout, if you put this code RsNLME and then this -W, it would zero out the price and you will get this for free. So this is an offer that is valid to mid-September, and I hope that if you are more interested in learning PML, that you go ahead and take advantage of that. Okay, so if there's any questions on logging in or getting access to that, just let me know. There's also a lot of recordings on PML that were done with Phoenix, but they're applicable here. And there's this PML school, this is complimentary, there's no charge for that you can also register for, and you will get a lot of examples with PML code. Okay, so I'm going to finish here. I know we don't have a lot of time, but I'll take any questions if you have questions, or give this back to Dr. Nieforth.
Thanks, Anna.
Are there any questions?
I think there's a couple of questions in chat, but in the interest of time, I think I'd like to continue on with the model fit. So we're sure to cover the core analysis, and we'll come to the questions at the end, if that's okay. Or Anna, you can take a look in chat and respond in chat.
Okay, I can do that. Actually,
I think, yeah. So in the slides you have, there's a couple of slides on generally getting help, both in R. You know, for any function in R, you can type question mark and then the function name. and a help convention will come up with a description, some example codes. These are in your slide deck, so take a look at these getting help slides. There's one for RsNLME and Piranha. In particular, I want to point you to the RsNLME vignettes that we're building. Now, these are beta versions, so there's websites that we still need to complete. These will all be done by December, but the one for RsNLME is in good draft form and is a great reference. And there's a bunch of other reference help references here too. So I'm going to show you this, and what I'll do next is jump back over to Piranha in the remaining time that we have. Now, we have our model, so the next thing we want to do is to fit that model. And Piranha makes this easy. You can right-click on the model and click Fit Meta Model. I won't run these in the interest of time, but we also have some Shiny apps that we covered the new meta model. That's the GUI that we looked at. There is a edit meta model, which will essentially open up this file in a text editor that will kind of check your code as you write it and let you know if there's errors. There's execute meta model, which brings up an interface for selecting different engine parameters, that type of thing. And we'll very quickly take a look at run initial estimates. So the initial estimates app allows you to take a look at the fit of your model based on what we specified as initial estimates. You remember I typed in 100 for volume and 10 for the clearances. So what this is doing is it's going to open my initial estimates app, and when it loads, basically I'm allowed to superimpose my model with my initial estimates over my data. So if I click on overlay, it'll show all the points. And then we have sliders in here. You can limit the time that you're looking at. Here we're looking out to the last observed data point, but here's my TVV. So maybe I want a little bit lower of a volume. I can drag that down and the curve immediately adjusts to bring that up a bit. You can look at individuals, step through, but you get the sense. You can kind of drag your estimates around until you're satisfied with the quality of your initial fits. Here I'm close enough, I'll hit save and exit. And essentially what I wanted to show you is what that did is it took the slider estimate that I had for my volume 1 and it put it in the model. So right now we're just going to go ahead and fit this meta model. Again, this brings up a window that is based on the configuration, but you can click go, and now we're running this model to fit it. I'm just extra window I'm going to close, sorry. So it's compiling the model compiled. It checks the licenses, and pretty soon it should run through the estimation. This is just a way to allow you to watch the progress of the run as it goes. This should run pretty quick, although I'm noticing things are running a bit slower because we're on Zoom. Here we go. Should be done very quickly. All right. Generating some outputs. Okay, it's complete. Now, again, you don't see anything here yet. You hit refresh. And okay, now it has some information about my base model. 100 subjects, 1,100 observations, my objective function, minus 1,900. There's some files that are output. Now, these files actually, you don't have to work with directly, because what we do is we basically use the expose package functionality to compile this output into an object that you can work with in R that facilitates both the creation of diagnostics for individual runs, but also comparison of diagnostics across runs. So you have some file output. It's not so interesting to like open this stuff up. You can if you like, but this is a useful tab here because this summarizes the results of the run. And here there is a little bug that we fix. If you ever come to the situation where you have estimates and your numbers are listed instead of your theta values, it's because there's an extra space after model. Again, this is a known bug. We fixed it for the next release. But if you just remove that space and refresh, then what you'll see is your theta value should populate. So we have volume, clearance, V2, CL2. This little bar graph tells you how far off from your initial estimates your final estimated parameters were. The value in parentheses is the standard error of your or the precision of your theta estimates. So here it's like volume is 90, but it could be 4% higher or lower. These are good standard errors. Same thing for omega. You have, how close you were to your initial estimates. You can look at the square root of these omegas. That's an approximation of the percent between subject variability. So you can just swap back and forth here. Again, the parentheses are the precision of that estimate. And then what we have in brackets are the shrinkage values. I think Serge may have touched on shrinkage. This is basically an indication of how much data is in your data set to inform these estimates. So when these numbers start to get large, by large, probably over 40%, what it's saying is that, hey Keith, you're trying to estimate a between subject variability on clearance, but your data set doesn't necessarily have information in the right places to inform that parameter estimate. So the estimate of 0.16433 is actually shrinking towards the population estimate. So yeah, I encourage you to look at papers on shrinkage, but it's a useful statistic. Probably one of the coolest features of Piranha is the scripts area. Let me maximize this. And here, we have basically sets of library scripts. These are built into Piranha that allow you to run diagnostics. And it's as simple as selecting your model and double clicking on the plot. And when you do that, I think I did it twice because things are a bit slow. Here I selected the combined goodness of fit plot, and here we have a nice combined goodness of fit. So here's my individual predicted versus observed, my population predicted versus observed. Here you're looking for general even distribution around the line of unity, which we see. It doesn't look too bad. These weighted residual plots, again, what you're looking for is even distribution around the line of unity. And these, we see a bit of a pattern. Remember I said we selected the wrong error model, the additive error model. What this is saying is that your residuals are larger, right, at the earlier times after dose. So when you see these types of funnel patterns and the conditional weighted residual plots, it's an indication that you might want to take a look at your model, your error model structure. And, here probably we rerun the model with a proportional error model. You'd see these plots improve. And that's something you can try on your own. I was going to do it, but in the interest of time, I think I need to move on. So that, again, I encourage you to, play with the built-in goodness of fit plots. You should be able to run, any of these for a given model. Make sure you're running the NLME ones, not the non-mem ones, and that you have the MMDL. But the last thing I wanted to show today is that for any of these plots, for example, DV versus IPRED, if I run this in R, we have this. Now, what you can do with any of these, I'm going to close this out, is right-click on it and say Open Script in RStudio. And what this will do, I'll just erase my lovely red plot there. Here is the code that we just opened from Piranha. And you can essentially highlight this all and run it. And what it'll do is it'll recreate the PDF. But what we want to do is take a look at the guts of that, which essentially, if you look at these scripts, at first they look confusing. All of this is pretty standard. And this part is just saying, okay, where's the model? What directory is it in? What are the estimates? That's standard for all these scripts. You don't have to worry about this part. Where you'll be getting into modifying is right down here in the plot commands. And let me just pick another one. I want to use an expose plot. So we have the basic plots are written in the lattice language. We also have the expose flavor of the same plots. So DV versus IPRED. I will open this in RStudio. And again, this is the ggplot version. So if I Control A and rerun this, I know I'm down to about 3 minutes, but I really want to cover this. So if you just bear with me. What you're able to do in R is modify this plot now. So if I go to my ggplot command, right, or my expose command, I should say, which is based on ggplot. It's just DV versus IPRED. And if I just run this right here and look at my plot, there's my plot, okay? Now, what you can do here is start to modify this. If you click question mark, DV versus IPRED, you'll get a help menu for that. And again, here's the usage. And these are arguments that you can provide. There's grouping, there's subtitles, there's captions. What you see here is what it uses by default. There's also faceting. Now, why is that useful? So this is the built-in plot from Piranha. But what if you're interested in faceting this plot by sex? It's as simple as just modifying that. And then you can hit run. I'll go back to my plot. And you see now we have, a plot faceted by gender. If we don't like the points, we can modify it. Again, this stuff is available in the help, but if I just change this, and so I'm just trying to give you a feel for, there's a type argument, and here I'm going to do points in a smooth only. So now if I rerun this, just trying to give you a feel for how you can customize these plots really quite easily. That looks a little bit cleaner there, right? Maybe I want to add some titles now. So I'm just going to copy from one of my slides, actually. Control C. I'm going to put a comma here. Control V. And now I'm using the title argument. And again, these arguments, they come from that help area. They're all specified in here. So question mark, the function, take a look at the help. There's usually examples, and you can just incorporate it directly into your plots. I'm using something in Expose that's very useful called template titles. And when you see the @ sign, like @y versus @x, @run, those are actually reserved variable names from within your run information that Expose knows what they are, pulls it, and then populates your titles with that. So here we have @y, right, is DV versus pred, right? And your run number, right? Run 1, my number of observations, 1100. I have a subtitle of the objective function value. And then down here, I have a path to where my work is. So that gives you kind of a sense for how to customize these plots. Of course, you can now save this plot. And then for any run, you could re-execute this to get this same plot for subsequent runs that you do in Piranha. So I think this is probably a good stopping point. I know we've been, today we're drinking from the fire hose a little bit. Again, you have the slide deck there. I encourage you to take a look at some of the reference help materials. It's a lot of material to cover. in terms of population pharmacokinetics in general, I did want to point out what I think is just an exceptional 3-part series from Diane Mold. Diane was actually my first boss at Roche back in the early 90s. But these papers really cover, concepts in population PK, and they're written in a very understandable way. So if you're beginning, to learn about population PK, I highly recommend this set of this set of papers. So I think I'll stop there. I know we're a minute over time, and perhaps let's see if there's any questions. Oh, you know what? I forgot. Homework.
Yeah, so I actually did put it on the chat as well. Again, we would strongly encourage you to stay. I know we are 2 minutes over. We may be about 10 or 15 minutes over today. Our intention is that you're powerfully set up to work on the homework assignments. And I would request Keith to actually walk us through the homework assignments. You will be getting a copy of this homework assignment in the next few hours, and we will also share today's video as soon as possible. I'll try to get that done, preferably in the next few hours as well, so you can start working on the homework assignments as soon as possible. Again, I do understand that we have covered quite a bit of material today. And as you're working through the homework assignments, you will get to understand the beauty of RsNLME and the ease of use of this particular tool. So go ahead, Keith, if you can please walk us through the homework assignment.
Sure. And again, I apologize for going over a little bit. It is quite a bit of material. So the homework basically, what it does is it's an assignment to have you step through what I showed today, essentially. There is a pkdata.csv data set. It's a 12 subject data set. Again, IV, drug X, and serial blood samples were collected for 24 hours. So, quite simple data set. And then I have a series of basically steps to, walk you through how you would approach this analysis in using RsNLME and Piranha. So the first question, as you basically open that data set, what you want to do is open the data set and put it in a directory of your choosing. Open Piranha, navigate to that directory, and then you should be able to see that under the Files tab. Again, just like we did here, navigate to the directory, make sure you hit refresh under Files. You should start with your data set like that. And then essentially what you're going to do is open that in the data inspector, okay? And there's 2 errors in this data set. And one of the assignments is to see if you can spot them. I'll be interested to see how people pick these out, because they are typical of the types of things that frustrate you. When dirty data is probably one of the most time-consuming elements of the pharmacometrics workflow. Next would be using the data inspector menu selections. So again, selecting the variables until you get a plot that you like, and then copying that ggplot2 code into R. It asks you to produce the following plot. Now, this plot requires you to modify that ggplot2 code a little bit. Shouldn't be too hard. There's a title, a couple of title changes. See if you can work with that to reproduce the plot here. Let's see, scroll down a little bit. Why can I not scroll down? Okay, and then of course the goal there is what would be a reasonable starting PK model. If you want, load this data set into ggQuickEDA and play with it. Again, I didn't want to make that a mandatory step, but something that I encourage you to do. Next step is to use the new model menu in the model builder to reproduce this model file below. Of course, the author is going to be different, but essentially this model syntax is what we're shooting for. 2 compartment with weight, gender, age covariates, some initial estimates. So see if you can use the model builder to reproduce that. There's a hint here, a couple of hints actually. You know, tells you how to get started. I won't cover that. Then you're going to fit the model, return the estimated values for, you know, clearance volume seal V2. Take a look at the precision of the terms. Are they precisely estimated? Maybe do some thinking we can discuss at the homework session, you know, thoughts around that. And then using the default diagnostic scripts in Piranha. This is just the default one. Produce this plot, and then really just explore the other built-in diagnostics provided with Piranha. And, you know, are you satisfied with the fit of your base model? So we can have, you know, again, a discussion. This is not intended to be like a really, you know, I guess in-depth challenging type of homework. Rather, it's to get you familiar with the core steps in the analysis. And then finally, I have you do what I just did at the very last example. Take the exposed DV versus IPRED plot and right-click it, open in RStudio, and then, you know, try to modify it using facet, custom plots, template titles, this type of thing, and see if you can reproduce this plot. That's really, again, I kind of focus on that because this is like why people use R, the ability to customize things exactly to your problem, because your problem is, it's never going to be exactly the same as something else, and it's the nature of the work we do. So that's the homework assignment. Again, I apologize for going over a few minutes. I will stop there.
Thank you, Keith. I mean, this was, again, quite a bit of material that was covered, and thank you for walking us through the use of RsNLME. I do want to acknowledge and appreciate all of our group heads who have been working through meeting their groups and helping them in solving the homework assignments. Again, a workshop of this magnitude would not have been possible without your contribution and support. Thank you again for everything that you are doing. We will arrange for a time to meet with the group heads so we can actually work on this homework assignments, so you become familiar and you have worked through the homework assignments, and then you can meet with your groups throughout the week and help them work on solving the homework assignment. The intention is that next week we would strongly encourage you to complete the homework assignment and turn them in. And next week when we meet, next Friday when we meet, we will actually be walking through these homework assignment like how we have done in the past. We would strongly encourage the participants to take on going over, or, you know, we will give you the opportunity to share your experience and explain how you solved the homework assignment. And Keith and Anna will be here with us. They can help guide you as you are sharing your answers. This will be helping you not only get a stronger concept and become more familiar with the tool, but also help your other fellow participants in being able to address the questions that they may be dealing with. Thank you again for all the group heads. Thank you again to all our volunteers who are making things possible. A strong shout out to Krishna, who has been instrumental in sending you all the email updates and also keeping you posted. I do see that some of the participants, I mean, we had a fewer number of people attending today. I would strongly encourage the group heads to reach out to your mentees to check with them on if they need any support. And we would like to see all of you back again next Friday.